international lab, now also at Zurek for 1 year, so this was a little bit easier to come here from Geneva than all the way from Berkeley. And she will basically give you 3 lectures about meta without prejudice.
So thanks very much for the invitation to come. It was great to walk in and see everybody so engaged with the tutorials. So I've been told that this is a pretty broad audience, so from master's students to beginning postdocs. So hopefully there'll be something for everyone in these 3 lectures, but we're going to start with the very basics. Okay, so this is what we're talking about, is the fact that we have this slice of the pie about 5 times as dominant as ordinary baryons, and we don't have a theory to describe it. There's also this other piece of the pie, the dark energy, but we don't actually know if this is new dynamics, or whether maybe it's a dynamical selection mechanism. On the other hand, we do know that whenever we're sitting here, it has to be physics beyond the standard model. And so let's just review why that is, because in order to piece together dark matter and try to understand what it is, we have to use the entire range of physics from the time that the universe is a second old, all the way until today. So, starting when the universe is a second old, when we synthesize nuclei to the time of CMB, when the universe is a few 100,000 years old, to the formation of large-scale structure, to the acceleration of the universe, to galactic rotation curves, all of these things together give this very beautiful, coherent picture that we're missing a lot of matter, that it's not all described by the standard model of particle physics. So because we're going to use each one of these pieces of evidence to piece together what we know about the dark matter, I want to just go through each one of these and how it is that we know from these pieces of evidence that we're actually looking for non-baryonic physics. Okay, so let's talk about the CMB epoch. So the first thing that you can ask, why particle dark matter? Why not something else? So for example, the first thing that people ask is, why doesn't it just happen to be baryons that are non-luminous? This is the first thing that people started looking for. Well, so first of all, we know that BBN and CMB together make independent measures of the baryon fraction. So from the rate at which these peaks damp in the CMB, that actually sets the baryon density in the universe at the CMB epoch. And then you can also compute the baryon to photon ratio and extract from the measurements of the helium and deuterium and hydrogen in the universe the ratio of baryons to photons. And you can see that what's preferred by the CMB and what's preferred by the BBN lie right on top of each other directly. Okay, so this is the first piece of evidence that in order to get the ringing of these peaks, okay, the frequency and the rate at which they damp, we need an additional piece of matter which is not strongly interacting. It doesn't interact with photons, okay, so it's not baryonic of some type. And the fact that it agrees with something that's at a much higher redshift tells us that we're looking for something that's not in the standard model. Okay. Then if you add on top of that, the measurement of the total curvature in the universe, okay, so the CMB measurement actually tells us from the location of this first peak that the universe is flat. The clusters measure very well the matter density in the universe. Okay, and then supernovae measures some linear combination. And the fact of the matter is that if you took away any one of these measurements, they would still be fully consistent with each other. So then the next thing that people ask is, okay, maybe it's not free baryons, because all these measurements agree with each other. Why not make the baryons non-interacting by binding them into some type of compact objects before the era of Big Bang nucleosynthesis? So you say, okay, it's some type of baryonic matter, but let's bind it into some large objects. And people spend quite a bit of time looking for objects like this, okay? So for example, if you have some distant star, and here we are on Earth, You can look for Kaczynski lensing, strong lensing, so you have a massive object which is transiting between the observer and some distant object. And by now, these days, usually these constraints are phrased in terms of a primordial black hole mass, but it's more generally a constraint on any macroscopic object made perhaps of baryons. And they look for these, and they're able to actually rule out quite a wide range. Okay, so here I've written 10 to the minus 8 solar mass. It's actually a little bit better, down at around 10 to the minus 10 solar mass. And this is the fraction of the dark matter that can be in compact objects of any form. And you can see that for this range from about 10 to the minus 10 solar mass and heavier, dark matter fraction in any type of compact objects is pretty well ruled out. Okay? And there's still this small window down here. Okay? This is an active area of research, how we can close this window. But nevertheless, it would seem that this is actually a pretty strongly constrained scenario. That's one statement. The next statement I'd like to make is that in order to actually bind baryons into objects of this size, you need new physics beyond the Standard Model. Okay? Certainly true that you need a phase transition or something like that in order to bind baryons into objects like this. At the very heavy end here, if the compact object is, say, about 100 to 1,000 solar mass or heavier, you would actually be able to see those compact objects in the graininess of the matter distribution. So that's what's shown here. This is the clumpiness of the matter. This is basically the matter power as a function of the weight number k. So larger k is smaller scales. And this is the point I want to make here is this is what's measured for the clumpiness of the dark matter. And if you add in additional compact objects of some mass, so here it's 1,000 solar mass or heavier, you can see that you amplify the clumpiness of the dark matter in a way that will be observable. And that's why this entire mass range above 1,000 solar mass is actually ruled out. So then the next thing you can say, well, maybe it's not free baryons, maybe it's not bound baryons, so then why don't we try to modify gravity? Okay. Now there's two reasons why I think that's not, well, there are actually many reasons, but let me just say two. Two reasons why I think that's not desirable. First of all, modified gravity theories tend to be sick. It's actually very hard to make a consistent theory that modifies the structure in general relativity. It's a very active, ongoing area of research. But I think the more direct answer to this is that it's never been demonstrated that you can get the entire range of the observations correct by modifying gravity. So typically, when people try to explain dark matter with modified gravity, what they try to get right is this one measurement down here at low redshift. They try to explain the galactic rotation curves by modifying Newton's law. But we also need to reproduce all of these other successful measurements that fit together like pieces of the puzzle. And it's never been shown in any theory of modified gravity how you might be able to do that. So these things together tell you that we actually have a pretty strong case for particle dark matter. Now, I wouldn't take this as a primary piece of evidence, but there's also this observation, as you know, of clusters of galaxies colliding with each other. So this is where the mass sits through lensing measurements, and this is where the gas sits, and you can see that there appears to be two centers of mass that just pass through each other, whereas the gas just gets stripped off. And this observation by itself can actually put fairly strong constraints on dark matter self-interactions. We'll talk a little bit more about that later. So I think the situation that we find ourselves in is something like a duck. Okay? You can say, if it walks like a duck and it sounds like a duck, and it looks just like a duck, it's probably a duck. It's the simplest explanation that we have for all the observations, both theoretically and from the testability point of view. Okay. So this is the working hypothesis that we're going to move forward with. So that said, once we posit that in addition to baryons, there's some form of dark matter that has relatively weak self-interactions. It has pretty weak interactions with the photons, and we're going to quantify what we mean by that as we go along. There are actually a very wide, as you know, very wide range of theories that can satisfy that. And this is a cartoon that often is shown. Dark matter particle mass is a function of the interaction cross-section. The most popular ones have been theories that have resided near the weak scale, or very light dark matter candidates. And so they sort of get lumped, I think, generally into two categories. One where you use the coherence of the dark matter particle itself, where its de Broglie wavelength is longer than the interparticle spacing. And theories where the dark matter behaves as in terms of the individual quanta, in terms of the individual particle, and not as a classical field. Now, there's an XKCD version of this cartoon that appeared recently, okay? Which actually, given that this the person who does this cartoon is not actually a particle physicist, gets things pretty well right. So here are the dark matter candidates. Axions, sterile neutrinos, here are electrons painted with a space camouflage. Neutralinos, by which we mean things that reside relatively here at the weak scale. Then there's sort of a gap here, okay, which he's populated with various things. And then primordial black holes are more generally compact objects, which tend to be, as we saw before, ruled out by a pretty wide range of observations. And I really like this quote. My theory is that dark matter is actually just a thin patina of brine covering the whole universe, and we don't notice it because we haven't thoroughly cleaned the place like eons. Okay. So we're actually going to spend in these first lectures time on this traditional dark matter candidate that sits near the weak scale. And we're going to talk about how you can build up more massive candidates, composite states up here at heavier masses. And then I also want to focus on this, it gets compressed here, but between a milli-eV and a GeV, there's about 12 orders of magnitude in mass that really have, up to this point, had very little theoretical attention or experimental attention, so I'll spend some time on that. And try to connect this entire picture together. Okay. So I said that the standard dark matter paradigm is that the dark matter is a single stable, weakly interacting particle that is completely neutral. But as people have started to look at dark matter without prejudice, so trying to step back from the paradigm of focusing on the WIMP and on the axion, they realized that what we could be looking for is a structure that's much richer. So the standard model, as we know, has a very rich structure. And up to this point, so the standard model has a ground state, sits around the GeV for the light baryon. But up to this point, we thought that the dark sector was pretty simple. So if I sort of imagine that there are some interactions, some barriers that separate the standard model sector from the visible sector, our thinking has shifted from the idea that we should focus on this very simple picture to one where you actually have some very complicated structure, maybe more similar to what's happening in the standard model. Still subject to constraints that we're going to describe about what the structure is in the dark matter sector. But still, if we discover a dark matter particle, it's really just the tip of the iceberg to uncovering what might be a very complex and interesting structure sitting over here. Okay, and so that's what I'm going to try to describe in more detail. Okay, so here's the program. So we're going to start with the basics. Okay, we're going to start basically with the tools for how one goes from the observations, which are macroscopic in nature, to a microphysical theory. Okay, so one of the basic things that we need to reproduce is the observed density in the universe and the cosmological history. So I'm going to start with just to put everyone on the same page, and if you've heard this before, which I'm sure most of you have, it might be good to just refresh yourself on the standard freeze-out paradigm. And then we'll go through these other cases, which freeze-in, asymmetric dark matter, freeze-out decay, misalignment, and then I'm going to talk about how you build up bigger objects through late universe synthesis. And then I'll spend some time on the sort of classic candidate, outlining how it is that one looks for supersymmetric dark matter, what are the features of it that are being constrained, both in direct and indirect detection. Then tomorrow, we'll look beyond the vanilla WIMP, we'll go through the motivations and the experimental search techniques, and then we'll talk about what these dark matter candidates without prejudice need to satisfy in terms of the observational constraints. Okay, and then we'll close with some of the recent things that people have been working on with new ideas in dark matter direct detection. Okay, so let's talk about paradigms for dark matter density. So as I said already, what we're trying to do is to connect a macroscopic observable to the microscopic properties of the theory that we're trying to reconstruct. So we're going to review these mechanisms, and again, keep in mind that what at the end of the day we're trying to reconstruct is a theory, which is to say, a Lagrangian. Okay. So thermal dark matter is based on the assumption that dark matter has strong enough interactions with itself that it stays in thermal equilibrium either with itself or with the Standard Model. So there's some type of interactions, I don't care what it is, that force its energy distribution to behave either Bose-Einstein or a Fermi-Dirac distribution. And so what that tells you is that if these particles remain in thermal equilibrium, the densities become exponentially suppressed at late time. So we know that the relativistic energy and number densities go like t to the fourth and t cubed. This is just the temperature in the universe, and then when it becomes non-relativistic, those things become suppressed by an exponential of the mass over the temperature. So I'd also like to comment that in general, we usually assume that the temperatures of the two sectors are the same, but there's not necessarily a reason that has to be the case. In particular, if the two sectors decouple from each other in the early universe, you can easily have two temperatures that describe the equilibrium distributions of the two sectors. And so, as you're familiar with, or most of you are familiar with, what happens is that if you plot the ratio of the number density to the entropy in the universe, where the entropy is just fixed to this t cubed density, then what happens if things remain in equilibrium is everything, as time goes on, just becomes exponentially suppressed. And so what you need is a departure from equilibrium in order to fix a density that's large enough to be consistent with the observable one. So, so this is the way this is done mechanically, and I'm writing this out explicitly because we're going to need it again later for the other cases, is the Boltzmann equation. So in the absence of any type of interactions, the Boltzmann equation, which just describes the evolution of the number density, dependent on the expansion of the universe. So I imagine that my universe is some ball of some radius a, and then I solve this thing, just that the Hubble expansion is a dot a. And then what I find is that in the absence of interactions, the number density just dilutes with the volume. Okay, so this is the simplest solution to it. So now what we do is to add in the microphysics. So this is the macrophysics, this is the microphysics. And it says that if the interactions are large enough, then what I will do is to have my number density follow the equilibrium number density. So now I just want to rewrite everything in terms of a more convenient variable. Okay, the ratio of this number density to the entropy, and that's what's done here. And so now, first of all, you can see why it is that the thing that sets, controls all the rates, is the ratio of the cross-section times the number density to the Hubble parameter. So always when you're doing a back-of-the-envelope estimate for whether something is in equilibrium or not, you compare n sigma b against the Hubble parameter. And this is the reason why you do it. It's just what you pull from the right-hand side of the Boltzmann equation. So y is constant if y is equal to y equilibrium. And then what happens is that y equilibrium drops precipitously, so that's when you're on the exponential part of this curve, when the mass is becoming greater than whatever the temperature is in the universe. You're dropping precipitously, and so then what happens is annihilation begins. Okay, so then you want, because this thing is dropping precipitously, then you really want to get rid of, you want to bring it back into equilibrium, so this thing is going to drop to go along with that, provided that the thing that's multiplying, sitting out front, n sigma v over h, is large enough. And so that, that happens as long as this condition holds, as I said. And so you continue to annihilate until that's no longer true. Okay, so then as sigma v goes up, then you stay in equilibrium longer. So you follow this exponential curve longer, the larger your annihilation cross-section is. Okay? And so this gives you all the information that you need. So now you can just solve this, and I want to get one number out of this because it's pretty universal. So we want to calculate the annihilation cross-section, which I've just told you that the number density, so that's rho on n sigma v is on the order of the Hubble parameter. And the Hubble parameter in the radiation-dominated universe just goes like the square root of the density. So it's t squared on n prime. Okay, so now let me just plug in for the number density here. And now I'm going to plug this in for whatever my observed energy density is today. So this is my macroscopic observable. And then I know dark matter is non-relativistic, so I'm going to redshift it back to the early universe when the annihilation process was happening. And so now all that I'm left with after doing this little bit of algebra is something that depends on an observable. This ratio of the mass to the temperature at freeze out, and the temperature of the photons today. That's all that goes in. Okay, so now I can, everything on the right-hand side now, this ratio I can actually obtain from solving the Boltzmann equation. And you can just see that on the previous slide, this number density goes like e to the minus m on t. There's some residual t dependence on the right-hand side, but it's only linear. So what dominates this equation is actually whatever this ratio is. So that number is pretty much fixed. There's some logarithmic dependence on what the freeze-out temperature is, but it's pretty much fixed. And so you know that this ratio is fairly model independent in the freeze-out scenario and is actually about 20. So that gives you all of the information that you need to plug in this. That just comes from freeze-out. It's pretty universal in freeze-out models, regardless of what scale it happens at. The density I observe, the temperature of the photons today, and so I can just plug these in and a number comes out. Okay, and it's 3 times 10 to the minus 26 centimeter cubed per second. Okay, so that's what I need for a microscopic annihilation process to get the observed density of dark matter in the universe. Okay, and so this number now, if I put in a dimensionful scale, okay, this has units of 1 on energy squared. When I convert it to natural units, is 1 on 20 TeV squared. So now I put in the weak coupling to the fourth, and divide, there should actually be a 4 pi there, okay? And the mass scale that comes out from this is 2 TeV. So if I have thermal, Vino, or Higgsino, electroweak doublet or triplet, so there are order 1 numbers floating around here that I haven't been careful about, the natural scale for that dark matter is about 2 to 3 TeV. And this is the reason why. It's just thermal freeze-out. I don't really have many knobs to dial. Okay? Are there any questions about this before I go on? Okay, everyone already knows this then. Okay. So that's what we aim for then, is to get that cross-section of around a few times 10 to the minus 26 centimeters cubed per second. So that's one way, is to have it drop out of equilibrium just by having the annihilations become not fast enough. Another way to stop the annihilation is to simply run out of antiparticles. This, in fact, is the way that it's done in the standard model. Why is it that we're made out of protons and not antiprotons, or electrons and not positrons? Because in the early universe, we had a T-cube number density of both. And the reason for that is that I had a small 1 part in 10 to the 10 more positrons than the electrons. They annihilated against each other to photons, and then the only thing I was left with at the end of that process was electrons. Okay, so this is what happens, positrons and electrons, they annihilate against each other, and I'm left with that 10 to the minus 10 number density by the annihilation process to photons. Now you can make the simple observation that I can do that just as well in the dark matter sector. If you allow the dark matter to have interactions which are new forces. Okay? So if you just say, just by fiat, that the only forces that the dark matter can couple to are the standard model forces, then this model does not work. But if you say that dark matter can also couple to its own force, and it can annihilate through that force, then this is a perfectly viable scenario. Seems very simple. So why might it be motivated, and what are the natural mass scales that would be associated with such a model? Well, we know observationally that the ratio of these two densities is about a factor of 5. And so if I now say that the number densities are related to each other in some way, then what this observational fact does for you is to relate the mass in the dark matter sector to the proton mass, and to put in this factor of 5. So those were this 5 GeVs. So a few GeV mass scale. Again, there are order 1 numbers that are floating around here. So how is it that one actually makes this work from a practical point of view? And there are 3 steps to making a model of asymmetric dark matter work. So first of all, if you want to relate the asymmetries in the 2 sectors to each other, what I need to do is to have some mechanism that shares the asymmetry. So that's step 1. And then if I want to retain the asymmetry in the dark matter sector at late times, in some way I need to decouple the mechanism that shares the asymmetry between the two, between, say, the baryons and the dark matter. Otherwise, what will happen is you'll wash out the asymmetry in both sectors. Okay, so that's step 2. So transfer, you want to share, decouple. And then the last step in this is to annihilate away the symmetric abundance, just like you do in the standard model. So you need a force in the dark sector to be able to accomplish this. So there are various ways of doing these 3 steps. And you can pretty much, I'm simplifying a little bit, but if you read the hundreds of papers on this subject, they really fit into one of 3 categories for sharing the mechanism. The first one is that you use some type of non-perturbative mechanism. So you can use sphalerons, for example. So we know that sphalerons violate B and L, they preserve B minus L. So what you can do is to have the dark matter somehow be charged to effectively carry baryon or lepton number, and in that way to have it shared between the 2 sectors. This tends to be strongly constrained or actually really ruled out by colliders. That's the first one. So the second one is higher dimension operators. So I have an operator that separately violates B or L or dark matter number, okay? But because it's a higher dimension operator, it decouples at low scales. I'll show you in a couple of slides how that works. And the last one is to have a particle that decays separately, that violates baryon and lepton number and dark matter number and decays into the 2 separate sectors separately. This is actually, in terms of the Lagrangian, it looks very similar to these models, but it has different dynamics. Okay. So let's look at how this works. So I said that the higher dimension operators are much less constrained than the sphaleron type setups, because if the dark matter carries electric charges, it's typically very strongly constrained by colliders. Okay, so how does this work? I have the visible sector, I have the dark matter sector, and now I'm going to represent this interaction between the 2 sectors as some kind of barrier here. And let's say, for example, that I have an interaction where the dark matter particle interacts with the neutron. So it's an up quark and two down quarks. So we know that we want the dark matter particle to be neutral. And so I need to couple it to some combination of standard model fields that is also neutral under the standard model gauge groups. And the neutron is one natural way of doing it. So I have an up quark and two down quarks. They're all right-handed, and the dark matter interacts with them. So at high temperatures, so this is a dimension 6 operator. It's suppressed by 1 on mass scale squared. At high temperatures, though, you don't care that it's suppressed by some mass scale because the interactions are very energetic. So just think of this like the electroweak interactions, like a Fermi, a 4 Fermi operator. You know, at very high energies, a Fermi interaction is not suppressed because you can produce the W and Z gauge bosons on a shell. It's exactly the same thing in the very early universe. You have a high energy collider, and the interactions are not suppressed because whatever is mediating it is not suppressed. I just don't see this barrier because I have such high energies to just slosh the baryon number back and forth between the two sectors. Then, as the universe cools, now I start to notice this barrier. Just like in the electroweak interactions, as the energy drops, the rates drop like E squared because of the heavy masses of gauge bosons. So that's what happens is the universe cools, and as a result, the two sectors freeze out separately, and I end up with a net baryon or lepton number in the standard model and a net dark matter number in the hidden sector. And so I can generalize this. I can write down any combination of standard model fields that is neutral under the forces, but carries baryon or lepton number, because I want to transfer that between the two sectors. So there are actually a limited number of operators I can write down in the lowest order. I can write down LH, so this is the left-handed doublet and Higgs doublet, two left-handed lepton doublets, and a right-handed lepton, QLD, and the neutron operator. Okay, so those are at lowest order, those are the operators you can write down that carry out baryon or lepton number and are neutral under the standard model forces. Okay, so you can see how this follows these steps. You share the asymmetry between the two sectors, you decouple just by virtue of the fact that it's a higher dimension operator. And now there's only one step left, which is to annihilate the symmetric abundance. So how does that work? So I guess I'm going to explain later on how that works. So as I said, you need some dark force, some force analogous to the photon in the visible sector. But what we're going to see later on is that there are constraints on the nature of that force, because that force will also mediate self-interactions. Okay, so we're going to actually learn something about the nature of the dark matter sector from this third requirement. Okay. So are there any questions about this? I don't believe you. Okay. So we'll move on to the next mechanism, which is freezing. So, incidentally, how far along am I? Halfway. Okay. So let's talk about late-time dark matter production. So this is a very different idea from the two previous ones. So the two previous ideas, dark matter was thermalized. It had strong enough interactions with itself that it carried this thermal number density, which at high temperatures was just went like a temperature cubed. So let's imagine the opposite extreme, that the dark matter has very feeble interactions. In fact, it has almost no interactions with the standard model or with itself. And let's imagine further that it's not produced in any way via inflation. So it doesn't couple to the inflaton. This sector is not populated in any way. Okay? So this is the starting point. It's the exact opposite point that you start from with thermal dark matter. And so there are two ways that you can produce this, or I should say two very well-known ways that you can produce this, through mechanisms known as freeze-in and freeze-out decay. So let me describe the freeze-in process. So I already said this, dark matter is not part of the thermal bath to start, and so as a result, what we say is that production is IR dominated. And what we mean by that is that at high temperatures, there's quite literally no dark matter, but as the universe freezes, as the universe cools, it is also freezing. As the universe cools, what you have is these very feeble interactions will occasionally spit off a dark matter particle. And so the picture is that there's a standard model bath, and no dark matter production, and you have this interaction now, this very feeble interaction that occasionally produces a dark matter particle. And so, in general, in order to make this mechanism viable, is you need a particular type of interaction where the production will be dominated at low temperatures. And there are many ways of doing this. I'll show you a couple. But what you need sort of is to have a production, so this is the number density again, the ratio of the number density to the entropy, that goes like some very small coupling constant squared, times, and what we'll see come out of this, the ratio of the Planck scale to the temperature at which it's produced. Okay, that's a big number, and Planck over whatever low temperature process is producing it, and as a result, we'll see that the typical couplings in the dark matter sector are extremely small. So let's go back to the Boltzmann equation and derive how this works. So it's the same equation as before. The change in the number density with the temperature goes like this interaction cross-section over the expansion of the universe, and then this difference between the number density and the equilibrium number density squared. So once again, you can do this rewriting of the variables that puts it in a little bit nicer form, and we're going to take the equilibrium number density now to be very small. And so we put in our usual scaling of the number density and the entropy to go like T cubed. And so now you just plug this thing in here, and we're going to take as our ansatz that the production cross-section is IR dominated. And so I'm going to have a dimensionless coupling constant squared divided by some total, this is like the center of mass energy squared. And so that's lambda squared on T squared. So this is just by 9-dimensional analysis. You plug that in here, and what comes out is that what was just on the previous slide, that the dimensionless number density goes like this coupling constant squared times m Planck on T. So what are some examples where this happens? So first of all, let me show you a cartoon. So the thing that we did at the very beginning was to take this dimensionless number density. So this is a freeze-out process. So this is the equilibrium number density, which is dropping like a rock. And so then you exit that equilibrium number density when you freeze out. So freeze-in, as the name says, is exactly the opposite. I start with effectively no number density of this stuff. And then because this interaction goes like 1 on T squared, I very feebly produce this thing and just gradually build it up until a point where the dark matter has frozen into a constant number density. And the next slide I'll explain why it is that you froze in. Okay. So here's a concrete example of this. So let's suppose we have a standard model fermion. Let's take it to be the electron positron. And just as a simple toy model, let's take millicharged dark matter. It doesn't have to be millicharged. It would just have to couple through some force that's pretty light in comparison to the electron. And so now I have a process where E plus E minus annihilates through whatever that force is to my dark matter. But now this coupling of this millicharged dark matter is extremely small. So if the millicharge, let's say for example, is 10 to the minus 10, this particle here never comes into equilibrium with the standard model. And furthermore, because this force mediator is pretty light, or in this case it could be exactly massless if you're really talking about millicharge, the cross-section for this will typically go like 1 on temperature squared. Okay. So this is what exactly applies here, and you can do the analysis of what is the effective coupling of the dark matter to this very light force in order to produce the observed density of dark matter. So here the dark matter is, say, an MeV in this range, and in fact this is why the slope changes, is because this is when you drop below the electron mass. And you find, in fact, that the coupling constant that you need is very, very small. Simply because what you're being balanced against is the Planck scale, which is to say the expansion is still relatively slow because the Planck mass is high.
Between the red curve and the blue dashed line?
Can you repeat your question?
We see the figure, there are two lines. One is the red one and one is the blue dashed one. And what's the difference between them?
I don't remember. You can, here's the archive number, you can go look at it.
I mean, I'll ask a question.
Yeah.
In your dimensional analysis, you said, okay, it scales Planck mass over temperature, but why Planck mass? Why not another mass scale?
Because it's the Hubble parameter that's sitting there. So you're still comparing, so this is, what you should see here is n sigma v on h is what's sitting in this. So this is a 1 on h that's sitting here. So what's happening here is there's an h on an h and then a t squared and a t cubed sitting upstairs. And so what you end up with is an n on t scale. Yeah. So it's really the fact that a larger Planck mass means slower expansion, which means that you need weaker couplings. That's the physics that's going into that. Okay. So this is the exact opposite limit from the freeze-out and from the asymmetric dark matter limit. Another thing that you can do is to have freeze-out decay. This is actually a very common way of setting. So freeze-in is actually also one way of setting the gravitino abundance. Yeah, there's another question back there.
Yeah, so you said that one of the assumptions of freeze-in is that the freezing particle isn't produced by an isotope. But it will be at least a one. So
yeah, so it doesn't need to be not produced. It just needs to be subdominantly produced.
I was just wondering if somebody has written down a specific example and just show that this holds in one scenario.
Well, the problem is that that's very unconstrained. I mean, I can do pretty much anything I want with the inflaton in terms of what sectors it reheats, right?
Sure. But even if one would
I mean, I don't even need to say that it's not produced at all. I just need to say that it's subdominantly produced in comparison to the standard model. And then it never thermalizes because its self-interactions are very small.
Sure, okay.
Yeah. But that's a good question. Any others? So the gravitino, in fact, is one example. Okay. Where you could, in fact, set the gravitino density through a freeze-in type mechanism. Another way of setting the gravitino density is through freeze-out decay. So in that case, you would have some states, heavier states, that have fairly strong interactions. They themselves have an annihilation process that freezes out. And then whatever that parent particle was that froze out, it then eventually decays. But the lifetime for decay is relatively long because the particle that it's decaying to, in this case the gravitino, has very, very weak interactions. In this case, the energy density that the next, so this it's called the S-WIMP, it's the next to lightest particle, is related to the number density or the energy density of the WIMP just by the ratio of the mass, let's say the mass of the gravitino to the mass of the particle that froze out. So this is another way of actually breaking the relation between the annihilation cross-section and the observed density of the dark matter. So lastly, even though I'm going to essentially scant time on axions, there's also the misalignment mechanism. So, and this is really just based on the universal fact that an oscillating field in a quadratic or close to quadratic potential has an equation of state that behaves exactly like cold dark matter. So you can see that just by writing down the energy density as phi dot squared plus this quadratic potential. And the pressure is just that kinetic energy minus the potential. And this thing will just have an equation of motion, which is an ordinary cosine. And so you plug that in here, and what happens is if this oscillation is relatively fast, the cosine squared gets averaged to a half. The energy density just goes like this mass squared times whatever the amplitude squared is. But the key thing here is that the pressure is 0. And the pressure being 0 is exactly what you need to have a cold dark matter equation of state. And this is the mechanism that sets the density for the axion, with the amplitude being set by Fa. But this is, of course, completely general. I can do this for any boson. In fact, I can even do it for a spin 1 particle. And people have recently started talking about production of spin 1 bosons that are a cold dark matter candidate.
Is it a coincidence that pressure and density are Legendre transform one or the other here?
Is it a coincidence?
Yeah, I don't know.
It's a consequence of the fact that it's a purely quadratic potential. So you have to, so to state it in another way, a purely quadratic potential means that the particle is free. So if it had interactions and the potential was some higher order, then the equation of state would not behave pressureless. Okay, so that's the physics of it. And so this just tells you that a particle that's free is pressureless, which shouldn't be surprising to you. Okay, so this is the summary of the paradigms for the dark matter relative density. So thermal freeze-out is the most commonly considered paradigm. And it's what's dominated really the search for dark matter at the Weak scale. It's this idea that dark matter pointed to a particular, the observed energy density of dark matter pointed to a particular mass scale because 3 times 10 to the minus 26 centimeter cube per second is 0.2 mass scale, which is 1 on 2 TeV squared. But it's also pretty easy to write down theories of dark matter that have a production mechanism in any one of these. And of course, this is, I'm not being complete here, okay? And these sets of production mechanisms really cover the entire range from about 10 TeV on downwards. So above 10 TeV, what happens is that in order to get that 3 times 10 to the minus 26 centimeter cube per second, the dark matter would need to have a coupling constant which is larger than 1, and then you start to run into various problems. Okay? So if the dark matter is heavier than about 10 TeV, it's not that you can't have a dark matter candidate there, you just need some other kind of mechanism to produce it. Now up here, we tend to have composite objects that have been formed, for example, primordial black holes. So I want to talk a little bit about what kind of dark matter candidate might live in this regime in between. And in general, what you need is some type of composite dark matter candidate. So cue balls are one example. Let me give you another example, which is just to take the standard model and remove electromagnetism from it. So what happens if I take the standard model and remove electromagnetism? So I still have the strong interactions, I still have the weak interactions, but I don't have any repulsive Coulomb force. And now let's ask the question, how big of nuclei would I synthesize when the universe is 1 second old? And this is actually a very easy calculation to do because it's the same calculation as the Boltzmann calculation, which is to just compute the rate at which nuclei are synthesized, depending on the interaction cross-section for making larger nuclei, their number density and their velocity. Okay? And this is just a number that weights this is essentially an interaction cross-section per n. Okay? So now I can plug this in. And the one thing I want to point out to you is that the presence of the Coulomb repulsion in the synthesis of nuclei puts in this exponential. that goes like the electromagnetic coupling constant n squared divided by a velocity. This is like a Sommerfeld enhancement. Okay? And then just these same factors. Okay, so what happens now if I solve this just in exactly the same way I would solve a freeze-out equation? Well, even with this very simple model, putting in a cross-section which is 100 GeV squared, because it's the strong interactions that are fixing that cross-section, and I just solve it, and what comes out is that I synthesize something that's very close to the deuterium bottleneck. Not very surprising, but I haven't really done very much work here, and this back of the envelope is the right answer. Let's just get rid of this factor, the Coulomb barrier. What happens if I get rid of the Coulomb barrier? Now all of a sudden I synthesize things all the way up to 10 to the 4. So it's actually a pretty big difference. So now let's just extend this idea a little bit further and say, okay, maybe my dark sectors may not just have standard model nuclei, but I have some other mass scale. A priori, it's free. So we put in a model where my dark matter is made up of nucleons bound together. The scale of this force is left free, and I remove any massless long-range force. That's also consistent with observations, because we know that dark matter in general doesn't look like it has long-range interactions. It would actually cause it to collapse to a disk, which is not consistent with observations. So what happens? Well, there's what's known as a compound nucleus model that allows me to compute the synthesis of these things. So these two guys come together, they thermalize with each other into this state, and it's in some excited state, and it settles down by emitting force mediators. And I can solve the same equation for the mass of the force mediator. So this is the analog of pions in the standard model, and the nucleon mass. So this is up here. These are contours of the mass of the dark matter particle. So the standard model without Coulomb interactions would have 10 to the 4 GeV. But you can see that if the dark matter mass scale was even somewhat different, so let's say it was sitting down here at a keV, still complete. So this is the mass of the force mediator and the dark matter mass. You can see that I can synthesize things that are 10 to the 20 GeV, 10 to the 24 GeV. So this is with a very moderate extension of the standard model. And I could populate this mass scale now from 10 GeV now all the way up to 10 to the 24 GeV. So 10 to the 57 GeV is a solar mass. So it's a 10 to the minus 27 solar masses or so. So these things are very, very massive relatively speaking. They start to become on the order of macroscopic objects. Okay, now all I had to do was to say that the nucleon mass scale in the hidden sector is slightly different, and the force mass scale is also somewhat different, completely consistent with all the observations. Any questions on this? So that was concluding what I was going to say about the paradigms for the dark matter density. I want to launch into the next section here, which is talking about supersymmetric dark matter and how it is that you set the observables in the dark matter sector. How am I doing on time? Should I stop or keep going?
You want to stop.
What?
We started close to 4, so we have 10 minutes for discussion, or you're starting to that.
So maybe I'll stop, and I can cover that case next time. So are there other questions or discussion?
I had a question about the use of the word, like, because it was never clear to me, Bose-Einstein condensate. So where you have a classical field, so it always implies that you have a condensate, like a Bose-Einstein condensate. You cannot always associate the temperature, right? I mean, like.
So what I typically mean by Bose-Einstein condensate is things are collapsing to the ground state. So if something has, strictly speaking, zero momentum, okay, then that's really, so let's contrast this with fermions. So what happens when I put a lot of fermions into a smaller and smaller space? That's precisely what's happening in this case when I synthesize nuclei. I'm stuffing more and more fermions into smaller space space, what happens? Well, they pick up a non-zero Fermi momentum, and the Fermi degeneracy pressure of that momentum is what supports the object. So what happens when I take a bunch of bosons and I stuff them into a smaller and smaller space? Well, they condense into a ground state where the momentum is very small. Now, in the case of axions, or in the case of any cold dark matter particle in the universe, nothing is ever completely in the ground state because gravitational effects give the state a non-zero momentum. Okay? But what we mean by Bose-Einstein condensate is just what I said, that the state preferentially sits in a very low momentum state, which is coherent.
I have a question.
Yes.
At the very beginning, you were discussing machos and also mentioned briefly the primordial black holes as potential dark matter. Can you come back to that later, or is that a time, or will you discuss that?
You mean the constraints?
Yeah, exactly. I mean, there's some revival of looking for machos, I understand.
Well, most of that I think has been driven by LIGO, or a lot of it has been driven by LIGO. And I wasn't going to wade into that debate, partly because there are so many different ways that window is pretty strongly constrained. So the revival in PDH interest has mostly been because there was this the extent to which you think this window might be open is controversial, around 10 solar mass or so. And there are various constraints on that, from Planck in particular is fairly robust. I wasn't going to comment on that in more detail. There's still this window open, so if you look at some of the older plots of this Subaru window actually extended all the way down here to much lower masses. But you can see that, so they think that this is not actually justified at very low masses, so they just sort of cut it off and said you should redo your analysis. And then there's some constraint from trapping the primordial black holes in the center of white dwarfs, which would cause them to detonate. It would cause to an early supernova explosion in these white dwarfs. And then there recently, and this is what this paper was about, was look again at femtolensing from GRBs at very long baselines. And I haven't read the details of this paper, but they also claimed that the previous analyses had not been done properly, that you have to be very careful about the way the waveforms behave, because it's essentially a double slit experiment. And their claim was that there were effects there that had not been taken into account, and therefore the current constraints were lifted. So there's another window that's currently sitting open here, and they claim that in the future this can be constrained. I guess I can spend some time discussing this. I wasn't going to. From my point of view, this is so in this mass window, you need various types of cosmological observations. Essentially, another thing that's actually going to be able to cover most of this range is pulsar timing arrays. So objects which transit so pulsars are very precise time. They pulse very precisely, or I should say, when averaged over very long time scales, the fluctuations in their periods don't fluctuate. So what you can do is to stare at these pulsars for a long period of time and wait for a gravitational redshift effect from a transiting object. And that can actually allow you to constrain most of this parameter space with future observations of pulsars, for example, from SK. So I wasn't actually going to talk further about that, although I could if there's popular demand. But essentially there are various types of, in order to get at these types of heavy objects, you need to use various types of gravitational lensing effects in various forms. And I think, asymptotically, can debate about this window, whether it's here or not. From my point of view, there are so many different constraints there that are pushing in the wrong direction that it's very unlikely that that LIGO is due to primordial light. It's sort of like, you know, how many horns do one put on a unicorn before? I mean, I think yeah, you would like to look for new physics, right? But we know that there are real astrophysical objects that produce events consistent with the LIGO signals. So I can either try to jump through 5 of these different constraints and say, well, maybe I can push here, maybe I can push there.
It's the duck question again, right?
What?
It's like the duck again. It looks
Yeah, it's like the duck. Yeah, it's something like that. Exactly, it's like the duck. Yes.
I have a question to what you said about the freeze-in mechanism. I said you pointed out that, I think you said that it's not really sensitive to the initial conditions. But don't you have a really heavy sensitivity on the reheating temperature?
Yeah, that was the question I was asked before.
Okay.
So the thing that you're assuming there is that the production, even the gravitational production or the coupling to the inflaton is subdominant to the standard model one. So the reheating in the dark matter sector is very subdominant to whatever is happening in the standard model sector. So that's, you know, you can model build that, or you can just put that by fiat and just say your inflaton couplings are such that the standard model sector gets reheated and the dark sector does not. So then you're starting with a set of initial conditions where the dark matter wasn't populated, and then it doesn't have strong enough interactions to be populated through its interactions with the standard model in the early universe. So essentially what you have to do is just wait for these very rare interactions to produce the standard model. But it is an assumption. Or I should say it's part of the initial conditions that go into the model. Yeah?
You probably mentioned it, but what prevents the compound nuclei from growing more?
So it's also a freeze-out process. Essentially what happens is they gobble up everything around. And then once everything is bound into one of these nuggets, okay, and they become, so the universe is expanding, of course. And so the number, as they become bigger, their number density goes down. And simultaneously, the universe is expanding. And those two things together mean that eventually this process will freeze up. So that's the calculation that goes into it. It's the same thing as what happens at Big Bang nucleosynthesis. In that case, there's an actual bottleneck because there's the Coulomb barrier, which suppresses the interaction rates. It makes it harder to produce it. Here, eventually, you run into just the rates become too small. So it's really just very similar to the freeze-out calculation, except you don't have an exponential drop, which is the reason why, incidentally, we can synthesize such large objects, because there's really not much of a barrier to just making things bigger. Yeah.
So then we have like nuggets of dark matter light. How does that influence to see the cosmic microwave background? Because like there is
so you need much bigger objects. So I mentioned before, if you have solar mass or 10 solar mass primordial black holes, those will affect the CMB spectrum, and you can place constraints on PPHs. But these things are still very, 10 to the 20 GeV is still on macroscopic scales a very small mass scale. So I didn't show this, but the strongest constraints will actually come from dark matter self-interactions, because now the interaction rate is now just set by the size. That's offset by the fact that the number density goes down as these things become so massive. But you can compute that rate and plot it. And that plot exists in the literature. I just didn't happen to put it in the slides. I can give you a reference if you're interested.
Maybe we should break here for coffee?
Sure.
And then, yeah, thank first of all. Half an hour, we continue to come. 3 or 15 minutes.